Hello and welcome to today's class on fluid mechanics. So in today's class, we are going to be talking about energy losses in pipes. Now, we all know that whenever fluid flows through pipes, it encounters some form of resistance, which leads to decrease or drop in the flow of fluid. Now, this decrease or drop in the flow of fluid causes what is called an energy loss, which can also be called head loss. Now, I've said when we talked about manometer or measurement of pressure using a manometer tube that fluid energy are usually measured or fluid pressures are usually measured in terms of heads. All right, so the energy loss can also be called a head loss. Now, in fluid flow, there are basically two forms of energy losses in fluid flow through a pipe. There are two forms of energy losses. The first is what is called the major energy loss, and the second is called the minor energy loss. All right, so we have the first energy loss, which is called the major energy loss. Okay, major energy loss, and the second is simply called the minor energy loss. Okay, now this energy loss can also be called, like I said, it can be called head loss. So you can also say major head loss or minor head loss. All right, so we have these two forms of energy loss, the major head loss and then the minor head loss. The major energy loss is actually loss due to friction. The major energy loss is the energy loss due to friction. As fluid flows through a pipe, it encounters some form of friction which reduces the motion of the fluid in the pipe. So that friction is what causes energy loss. Now, energy loss due to friction can be calculated using two formulas. The first formula is by the use of Darcy-Weisbach equation, and the second formula is the Chassis formula. So to calculate the energy loss due to friction, we simply use one Darcy-Weisbach equation. Okay, Darcy-Weisbach equation, and the second formula is called the Chassis formula. The Chassis formula. So these are the two major formulas we use in calculating energy loss due to friction. Now, let's talk about the Darcy-Weisbach equation. In the Darcy-Weisbach equation, that's the first one, Darcy-Weisbach equation. All right, so in this equation, the formula is simply head loss due to friction, HF, is now equal to 4FL. Okay, this is 4FL V squared all over D times 2G. So this is Darcy-Weisbach equation where HF stands for head loss due to friction. Okay, head loss due to friction. All right, so HF stands for head loss due to friction. Now F here stands for the friction factor or the coefficient of friction. F stands for coefficient of friction. All right. So F stands for the coefficient of friction, L stands for the length of the pipe, V itself stands for the velocity of flow, whereas D stands for the diameter of the pipe, and G is constant, gravity, and of course, G has a value of 9.81 meters per second squared. That's a constant value, gravity. Now, it means that in order to make use of the Darcy-Weisbach equation, we need to know what the friction factor is or the coefficient of friction is. We need to know what it is. Now, there are two major ways of calculating the coefficient of friction if it is not given to you. If you want to employ the Darcy-Weisbach equation without being given the coefficient of friction, there are two major ways of finding it. The first way is the coefficient of friction itself, which is F, can be determined using the formula 0.0791 all over Reynolds number to the power of 1 all over 4 for turbulent flow. When the flow is turbulent, you can find the coefficient of friction using this formula. So, and you know that in turbulent flow, we simply mean that Reynolds number must be equal to or greater than 4,000. So if you have the Reynolds number to be equal to 4,000 or larger than 4,000, then we are simply saying it is what? A turbulent flow. It is a turbulent flow. All right, so for turbulent flows, we simply use this equation to find the value of the coefficient of friction. So all we need to do is obtain the value of the Reynolds number. And of course, I've done a video on laminar and turbulent flow showing how to find the Reynolds number, whether it is laminar or it is turbulent. And the equation for Reynolds number remains Re equals rho Vd all over mu, or it can also be Vd divided by kinematic viscosity. Okay, so I've done a video on this already, so please do well to look up compressible flow on my playlist on fluid mechanics for proper understanding. But then you can employ either of these formulas to calculate the value of the Reynolds number, then check if it is turbulent. If it is turbulent, it means to find the friction factor, you use this equation. But if it is laminar, then friction factor, if it is laminar, is now equal to 0.16 divided by the Reynolds number. This is now for laminar flow. When Reynolds number is less than or equal to 2000, that's the laminar flow. Okay, so if the flow is laminar, then to find the friction factor, we simply employ this equation. So in both equations, all we need to do is to what? Find the values of the Reynolds number using this equation. Then check if it is turbulent or if it is laminar. Impute into any of the equation depending on whether laminar or turbulent. Then obtain your friction factor. Of course, the length of the pipe will be given to you. The speed of flow will also be given to you. Diameter of the pipe will be given to you. You can use it to find head loss due to friction. All right, so that is how to employ the Dicey-Weisbach equation. I will do a separate video on that, calculating using Dicey-Weisbach equation and the Chassis formula. This is just an introduction video on energy losses in pipes. So the second way to calculate the head loss due to friction, like I said, is by the use of the Chassis formula. So what is now the Chassis formula? So let's talk about the Chassis formula. The Chassis formula is simply V is equal to C root M I, okay, where V, of course, is the speed of flow or velocity of flow, and C is called the Chassis constant. It will always be given to you. C is called the Chassis constant. Now, M can be determined from the formula area of pipe all over wetted perimeter, and this can be given as the area of the pipe. Of course, you know area of pipe. Okay, this can be given as simply A all over P. All right, so this stands for M, A all over P, where A itself, which is the area now, is pi diameter squared all over 4. That gives us the area of the pipe. And the perimeter itself, P, is simply what? Pi times diameter D. Now, if you divide these two together, you're going to obtain that M is equal to pi D squared over 4 all divided by pi times D. So notice that pi cancels pi, D cancels one of these D squared. You are now simply left with M to be equal to D all over 4. So you don't need to know these formulas. You don't need to know all these approaches. Just have it in mind that if you're given a pipe of diameter, to find M using the Chassis formula is simply what? Diameter divided by 4. That's how you obtain your M. Now, but the aim is to find head loss due to friction using the Chassis formula. Now, that head loss due to friction actually lies in I. I is simply called slope. Okay, this I is called slope. So most textbooks actually use S in place of I. So if you go through some textbooks, you see something like C root MS. Okay, it's still the same thing as I. It means slope. Now, what is this slope? I is equal to head loss due to friction all over the length of the pipe. So the head loss due to friction actually lies in I. So from here, to obtain the head loss due to friction using Chassis formula, it is simply what? Cross multiplying. The length multiplies the what? Slope. So you simply have L times I. Alright, so this gives you the head loss due to friction from Chassis formula. So which means the whole attempt is actually what? From this formula, you make I subject of the formula. From the whole equation, you have to make I subject, then you cannot find HF using this formula, length times I. But then how do you make I subject? If I have velocity to be equal to C root mi, it means that if I have V to be equal to C root mi, it means that if I want to make I subject, I need to first of all what? Remove the square root here. That means I have to square both sides. Okay, I have to square both sides. If I do that, I have here now v squared, and that's equal to, remember, this is also under the influence of these two. This is also under the influence of these two. Therefore, it becomes, or this square, sorry, therefore it becomes c squared, and then this squared cancels this square root. You're left with what? M times I. Okay, you have it. So from here, you simply make I subject, which is the slope. Slope is now equal to velocity squared all over c squared times m. All right, so this is how you find the value of your slope I. If you have the velocity, the chases constant, and of course m is a constant, you can always find it using that relationship. All right, guys, so these are the two major energy losses that exist in any fluid flow in a pipe. Like I said, we have a major energy loss and we have the minor energy loss. The major energy loss are usually caused by friction, and we have two equations to calculate for the major energy losses, which is the Dijsselbroek equation, which I've talked about, and then the Chassis formula, which I've also talked about in this particular explanation. All right, so we are going to move into the minor energy losses. Now, there are about 7 minor energy losses, or 7 things that constitute the minor energy losses in fluid flow through a pipe. We have energy loss due to inlet of the fluid or entrance of the fluid into the pipe. We can have minor energy loss due to sudden enlargement of the pipe. We can have minor energy loss due to sudden contraction of the pipe. We can also have minor energy loss due to exit of fluid from a pipe. We can have minor energy loss if there is an obstruction in the pipe. It's called energy loss due to obstruction in the pipe. We can also have minor energy loss if there's a bend in the pipe. Okay, if the pipe is designed in such a way that there's a bend, then it constitutes a minor energy loss called energy loss due to bend. Also, we also have energy loss due to pipe fitting. Depending on the kind of fitting that is there, it can also constitute a minor energy loss called energy loss due to pipe fitting. All right, so let's take this off now and explain all the minor energy losses involved. Welcome back. All right, so I said we have about 7 energy losses which constitute the minor energy loss. Now, let's start listing them from the very first. The first energy loss, which makes up the minor energy loss I'm going to be talking about, is what is called the energy loss due to entrance, of fluid. All right, so let's say we have a pipe. Okay. Let's say we have a pipe of this manner. Let's say we have this pipe and fluid flows through this pipe from here. Now, the intensity of the fluid which comes in from here, as this fluid is entering into the pipe, it experiences a reduction or slow in speed. Now, that reduction or slow in speed causes or constitutes what is called the energy loss due to entrance. And energy loss due to entrance is simply given from the formula as HI. I means inlet, and that is equal to 0.5 V squared all over 2G. Now, this value V depends on the velocity of the inlet. So if the entrance is V1, if the speed of flow at the entrance is what? V1, which is initial speed as the fluid enters into the pipe, then it means that inlet head loss is simply what? 0.5 V1 squared all over 2G. Where G is constant, gravity, V becomes the speed of flow as the fluid enters into the pipe. So as a fluid enters into a pipe, it experiences a reduction in flow. That reduction in flow is what causes what? is what causes the head loss due to entrance. And we use simply this formula to calculate head loss due to entrance. So V1, if the entrance is at V1, of course, if the speed of flow is V1, initial speed from the entrance, then we use this equation 0.5 V1 squared all over 2G to calculate head loss due to entrance of fluid. Now, it is very important for us to know that as fluid flows through a pipe, is not just the minor energy losses that takes place, major energy losses, especially energy loss due to friction, also takes place in, of course, the pipe. Because what is friction? We already know that friction simply means when two bodies are in contact, friction is bound to occur. So the fluid entering inside the pipe is in contact with the surface of the pipe. So we also have what? A major energy loss due to friction. So aside the energy loss due to entrance, if this fluid enters into this pipe, of course, it also flows with this same speed, V1, because this is the very first pipe that encounters the fluid, okay, as the fluid enters. So it still flows with this same speed, V1, inside this pipe. Now, since there is now a contact between the fluid and the surface of the pipe, then we should have a major energy loss caused by friction. Now, that is not a type of minor energy loss, but it is something that you have to keep in mind. After the energy loss due to entrance, the next thing to calculate is the major energy loss due to friction. And the best equation to use to calculate that is by the use of the Dicey-Weisberg equation. All right, so I'm just going to put an asterisk since it's not a minor energy loss. So it's just for you to keep it in mind that after calculating the energy loss due to entrance, the next thing to find is immediately the fluid is inside the pipe, we have to find the energy loss due to friction. So energy loss due to friction using the Dicey-Weisberg equation. And of course, from Dicey-Weisberg equation, you know that HF is equal to 4FL V squared. Now, V1 squared because the same speed enters into this particular pipe. So it becomes V1 squared all over D times 2G. Okay, this is 4 once again. All right, so this becomes the head loss due to friction as the fluid enters into the pipe. Now, notice what happens. The diameter of this pipe is quite smaller compared to the diameter of this pipe. So, which means that as this fluid flows out from this pipe and enters here, it is going to observe what? A slow in speed. The speed will reduce and we simply call that speed V2. The speed of the fluid will actually what? Reduce. Now, since this speed reduces, because it needs to make up for all these spaces, if it keeps going in this manner, it means there will what? Leftovers here. If this fluid flows in this manner, it means we are going to be having leftovers here. So this fluid, since it's fluid, of course, it has to fill up what? The entire surface of the pipe. And in so doing, the speed will reduce. And since there was a sudden enlargement as the fluid moves from here down to this point, there was a sudden enlargement to a larger diameter pipe, then we have another minor energy loss, which is called energy loss due to sudden enlargement. So the second minor energy loss we're talking about is energy loss due to sudden enlargement. Sudden enlargement. Okay, energy loss due to sudden enlargement, and the speed of flow in that particular larger pipe is what? V2. Therefore, the energy loss due to sudden enlargement, take notes, can be calculated using this formula. HE equal to, E here stands for enlargement and H stands for head, of course. So H is equal to V1 minus V2 all squared all over 2G. So we use this formula to calculate the energy loss due to sudden enlargement. All right. So now, as the fluid enters through this pipe, if there is no other pipe or any other thing connecting this fluid, that means the fluid will exit this pipe. Okay, since there is no other pipe or a tank where this fluid will discharge, it means that the fluid will exit this pipe. And if it is exiting the pipe, it is also exiting this pipe with what? This same speed, V2, because this is the speed which it has in this particular pipe. So if it is leaving this pipe, it is also leaving this pipe due to what? This same speed. Now, the energy loss at this point is called energy loss due to exit. Okay, so we have another energy loss there. That's the third minor energy loss called energy loss due to exit. Just like we have energy loss due to entrance, we also have energy loss due to exit of fluid. Energy loss due to exit of fluid, and it is symbolized as HO, O for outlet, just like HI, I for inlet. Okay, HO is now equal to, the formula for this remains V all over 2G. V squared all over 2G, sorry. Now, the v squared depends on the type or the particular velocity which is exiting. But in this case now, the velocity exiting is what? V2. So the pipe could be more than, we could have a series connection of different types of pipe, okay, all joined together. So they will move at different speed to one another. So since this is V2, that means we can also call here to be V2 all squared divides by 2G. So this represents the energy loss due to exit of fluid in the pipe. Okay, so that is just a little analysis considering this situation. Now, let's say we are taking a reverse mechanism. Let's say we are considering when the fluid flows in a reversed mechanism. Okay, that will constitute another form of energy, which is number 4. But then, before we talk about this, let's explain it using this same diagram. Let's now imagine that this fluid is moving backwards. Okay, let's explain. Okay. All right, so let's now imagine that this fluid is moving in this manner, is moving backwards. So I have a fluid flow. This becomes my initial speed, V1. So if this fluid enters into this pipe, of course, it's also going to move with this speed, V1. Okay, so the first thing we did also holds, that's inlet energy loss due to entrance, or inlet energy loss. That one also holds. As the fluid enters into the pipe, there is friction, so we calculate energy loss due to friction using the Weisbach equation. Now, if this fluid is in this pipe and this fluid wants to enter into this pipe, notice that there is now a reduction in the size of the pipe. This pipe is larger in diameter, whereas this pipe has a very small diameter. So which means this the fluid particles in this particular pipe will have to squeeze themselves and of course move at a very higher speed to be able to what? Exit or enter into this pipe or enter through this pipe, because of what? A decrease, which is called sudden contraction. There is now a contraction in the diameter of the pipe. This diameter is larger than this diameter, so there is now a sudden contraction in the diameter of the pipe. So if this is V1, which entails inlet velocity, then the velocity as the fluid enters into this pipe is going to be different, because it can't be the same speed. This will move at a higher speed than this particular speed. So we can call this velocity V2. But due to the contraction in pipe, it will constitute another form of energy loss, which is called energy loss due to contraction. All right, so that will give us the fourth energy loss, called energy loss due to contraction. Energy loss due to contraction of pipe, due to contraction of pipe. All right, so we have the energy loss due to contraction of pipe, and we can calculate this using the formula HC. C stands for contraction, is equal to 0.5 V squared all over 2G. Now, V represents the speed at the contracted region. The speed at the contracted region. So in this case now, it is V2. So we can simply say this is 0.5 V2 squared all over 2G. So we'll simply use this formula to find the energy loss due to contraction. Okay, so aside from these four energy losses we've talked about, we can also have, if there's a bend in the pipe. Let's say this pipe has a bend, something like this. Let's say this pipe has a bend. Okay, if this pipe have a bend, then there's also going to be what? Some form of reduction in the fluid flow due to this bend. There's going to be some form of reduction in the fluid flow due to this bend. Therefore, this bend constitutes another form of minor energy loss, which is called energy loss due to bend. Okay, so we can have another energy loss called, that's the fifth minor energy loss, it is called the energy loss due to bend. Energy loss due to bend. Okay, so if there's a bend on any part of the pipe and fluid flows through that bend, then it's going to reduce the intensity of energy which the fluid is flowing with. That will constitute a minor energy loss, which is called energy loss due to bend. And the formula to calculate that remains HB. B stands for bend, H represents head or energy loss, and that's equal to K v squared all over 2g. So v depends on the particular velocity at the point of bend. In this case now, it is still v2 that enters here and experiences what? This bend. This is v2. Therefore, you can simply say or rewrite this equation as k v2 all squared all over 2g. So this is the formula we use to calculate for the head loss due to bend or energy loss due to bend. Now, K there stands for the coefficient of bend. K stands for the coefficient of bend, and of course, it depends on the radius of curvature. Yes, it depends on the radius of curvature and diameter of the pipe or the angle of bend. Of course, we always have 45 degrees angle of bend. We also have 90 degrees angle of bending. Okay, so the K value there stands for the coefficient of bend. It depends on the diameter of the pipe, radius of curvature of the bend, and of course the angle of bend. That's what K there depends on. Okay, so aside from that, we can also have pipe fitting. Okay, if there's a fitting on the pipe, if there's a fitting on the pipe, as fluid flows through that particular fitting, of course, that fitting will constitute another type of energy called energy loss due to pipe fitting. So if you have different kinds of fitting, it will also constitute another minor energy losses. Okay, so we've talked about five there. The sixth is called energy loss due to several fitting. Energy loss due to several fitting. Okay, and to calculate that, we also make use of the formula HF. F stands for, okay, FIT, fit, head loss due to fitting, and it can be calculated using the same formula K V squared all over 2G. So V depends on the particular velocity at the point of the fit. Okay, if it is V1, then it becomes V1 all over V1 squared all over 2G times K. If it is V2, depending on the speed of flow at the point of the fit, we can use this particular formula to calculate the energy loss due to several pipe fitting. Okay, where K, of course, is called the coefficient of fit. K is called the coefficient of fit. It depends on the type of fitting, pipe fitting, which is involved. K is called the coefficient of fit. Now, the final energy loss, final minor energy loss, which takes place in a fluid flow, is energy loss due to obstruction. So, if there was an obstruction, let's say in this pipe, we had a stone. A stone could constitute an obstruction. Let's say in this pipe we had a stone present in the pipe. As the fluid flow, what happens is that this portion of the fluid at this point will have to divert to this point, divert to this point. Same thing happens, divert to this point. So that will reduce the intensity of flow and also bring about a decrease in the energy of the fluid. All right, so if there's an obstruction in the pipe, then we have what is called energy loss due to obstruction. And that is the final type of energy loss. Okay, let me take this off. All right, so 7 is called energy loss due to obstruction. Energy loss due to obstruct. All right, due to obstruction. So if there's an obstruction in the path of fluid flow, it will cause a decrease in energy. That will cause a loss of energy in the fluid. Okay, so we call that energy loss due to obstruction, and to calculate that, we make use of the formula head loss due to obstruction is equal to A all over CC into A minus A all squared multiplied by V squared all over 2G. So once again, V stands for the speed of flow at the point where the obstruction is found. So in this case, if this is the entrance with a speed of V1, that means the obstruction is found at where with a speed of V1. So that means you can write this as in by calling this velocity V1. But A here stands for area of the pipe, same thing as this area of the pipe, while this small letter A stands for the area or the maximum area of the obstruction. So the given object which is causing an obstruction should have a diameter, and if it has a diameter, you can constitute the area of that particular object causing the obstruction. So this small letter A stands for the maximum area of obstruction, and CC, of course, is a constant which will also be given to you. And okay, like I said, V depends on the speed of flow at the point of the obstruction. So that's the formula to calculate the head loss due to obstruction. So in all, I said that we have two kinds of energy losses as fluid flow through a pipe. The first energy loss is called the major energy loss, which is caused by friction. And there are two basic formulas to calculating the major energy loss. Like I said, we have the Darcy-Weisbach equation and we have the Chess's formula. And then I said the minor energy losses, there are seven different energy losses which constitute the minor energy losses. And we've highlighted all of them here. Energy loss due to sudden enlargement, energy loss due to sudden contraction, energy loss due to entrance, energy loss due to exit, energy loss due to bend in the pipe, energy loss due to pipe fitting, energy loss due to obstruction in the pipe, and of course, and that is the seven different energy losses which we've talked about here. But these energy losses came from an equation which is called the Bernoulli's equation. So I've done a video on Bernoulli's equation. Do well to watch it up for proper understanding. The whole energy losses came from the Bernoulli's equation. How? Now, let's recall the Bernoulli's equation. Okay, so we've done that before. I'll post a link on that video on the description of this particular video. So do well to watch it or go through my playlist for proper understanding. But then we gave the Bernoulli's equation. Okay, and we simply said the pressure head, call this P1 all over W, plus the kinetic head V1 squared all over 2G plus the potential head Z1 is equal to the pressure head P2 all over W plus the kinetic head V2 squared all over 2G plus the potential head Z2 plus losses. Okay, so if you have losses on the second part or a fluid flow in a pipe, then employing the Bernoulli's equation, you have to add all these losses, okay, on the other side of the equation. So you add all these losses. Now, what are these losses? These losses constitute the minor energy losses, which we've talked about, and the major energy losses as fluid flows through a pipe. The major energy losses and the minor energy losses are what constitutes here. So this simply means that I can write this equation as P1 all over W plus V1 squared all over 2G plus Z1, and that's equal to P2 all over W plus V2 squared all over 2G plus Z2 plus, now what are these losses? Head loss due to enlargement, head loss due to contraction, head loss due to inlet or entrance, plus head loss due to exit or outlet, plus head loss due to bend if there's a bend in the pipe, plus head loss due to fitting if there's a fitting in the pipe, plus head loss due to obstruction, and plus head loss due to friction. All right, so in all, this becomes the Bernoulli's equation. So whenever a problem is given to you, okay, on this particular subject matter, talking about determining energy losses in fluid, we have to, of course, employ the Bernoulli's equation. We have to make use of the Bernoulli's equation. Now, if the pressure was not given to you, automatically this becomes zero. If the speed of flow was not given to you or kinetic energy was not given to you, automatically this becomes zero. But whatever is given to you, if pressure is not given to you, this becomes zero. Also here, this becomes zero. But then if the height of the pipes are also not given to you, of course, you can also neglect them, they become zero. But in all, whatever is given to you, you have to employ the Bernoulli's equation and solve. Another important equation to be employed solving for energy losses is what is called the continuity equation. I've also done a video on this. continuity equation. Just go through my playlist on fluid mechanics for proper understanding. All right, so I've done continuity equation. And what is continuity equation? Is an equation that governs discharge of fluid flow in a pipe. And the equation is simply saying that the discharge of flow at entrance equals discharge of flow at exit. So if this fluid is entering here, it enters with a particular discharge called that Q1. And if it is leaving here, it leaves with a particular discharge called that Q2. But from continuity equation, these two discharges, Q1 is equal to what? Q2. That's continuity equation. And what is discharge? Area times velocity. That gives you the discharge. The intensity, rate of flow of fluid through a pipe is called discharge. All right, so this is simply saying that the area of pipe 1 multiplied by the speed of flow of pipe 1 is equal to area of pipe 2 multiplied by the speed of flow of pipe 2. So from here, you can either make V1 subject, or you make V2 subject, or you make V1 subject in terms of V2, and vice versa. So far you have the diameter of the pipe, you can always constitute or find their area. So these are the three basic equations which govern all calculation in energy loss due to in the pipe flow, okay, or due to fluid flow in a pipe. All right, guys, so I'll pause the video here. In the next video, we are going to be applying everything we learned here to do analysis or calculations. I will see you in that video. Thanks and cheers.